There was a click sound. I'm not sure what that meant. Claire, if you're seeing this later, it's Friday. We didn't record anything yesterday. Sorry. Hope you're feeling better. If you're not seeing this later, it doesn't matter what I say. I guess you'll see it later. Hey, look, Claire. Your friends are here. Your two classmates. There they are. And the surface I'm using to record this is right on your desk. Gives you the proper perspective. Now, yesterday, this is a quick review. I'm not going to go over all the reasons why, but we came up with equations for V right at the end of, didn't we? Come up with an equation for V. Mm-hmm. The definition of V is U over Q. And is that showing up? Probably. If you have two parallel plates that are charged, so there's an electric field between them, and if you place a proton here, it has potential energy due to the field. Because if you just let go of it, it would move to the right. So it has potential energy, that's what the U is, and that potential energy would then start to turn into kinetic energy as it moved across, and it would stop over here. If you took a proton here and wanted to move it back, that would take work to get it back over there. And so we talked a little bit about the conservation of energy, that the work to move it to the left is equal to the potential energy it has when it's over on the left, and that's equal to the kinetic energy it would have if you let go and it moved to the right. Conservation of energy. All right, but then none of that's about V, all that's about energy. Then we talked about potential, Potential. We talked a little bit about that last year. The symbol is V. V also stands for the word voltage, and it's defined this way as potential energy per unit charge, and I think we were talking about that at the end of the period yesterday. So the concept is this: if there's a point here in the field, even if nothing is placed there, there's a point there that has a V, has a certain V. Its V is because of the field. Now, if we're going to use that equation to calculate it, though, we have to put something there, because the U and the Q are for the test charge. So you have to put something there to use that equation. But even if you don't put a test charge there, there's still a V because of the field. Anyway, if I put a proton there, then U would be the potential energy of the proton, whatever that is, and the Q would be the charge of a proton, which is the elementary charge. And so you could actually calculate what V is right there if you knew those two things. Now, the point of the definition, though, and this is the definition right here, that's the definition of potential. The point of the definition is that V does not depend on what you put there. You could put a proton there, but you could also put a particle that has a whole lot of coulombs on it, and you would get the same V. V depends on the place it is in this electric field. It doesn't depend on the test charge, because if you put something that had more charge on it, the Q was greater, it would have more potential energy, and so you would divide and still get the same thing. So V is something that does not depend on what you place there. In fact, if you place nothing there, you just have a point P, it still has a V. Yes?
If potential energy is like the amount of work it took,
right?
If something that you put there is bigger, doesn't it take more force than like more work?
Yes, so it would have more potential energy. So yeah, if you put a bigger charged particle over here that had more charge on it, and you pushed it over, it doesn't have to be bigger. If it has more charge, it would take more force to push it against the plates, right? So it's going to take more force. But if it takes more force, it's because it has more charge. So that would be greater, but so would that. It's not going to really take more force because it's heavier. The kind of particles we talk about here I guess you could say if you're accelerating it, if you're pushing it, speeding it up, that would take more force for a greater mass. But we're not, we're just moving it. The minimum force, which will be a constant speed across, that's gonna be all due to the field. And how much the field pushes against it. So these plates are not changing, so if it has more Q, it would take more force, and that would be more U. So you'd still divide and get the same V. Now, the V is not the same at these different points here. And you can look at that and tell if you took that proton and just pushed it at this point, here it doesn't have as much potential energy as it does over there. It has less, and so the V is less over here. So the V is maximum over here, and it gets less and less and less until over here the V is 0. That's not always true that it's 0, but it's always less. There's always a potential difference between here and here, where this is greater potential than that is. Okay, so sometimes you'll see the expression delta V. This is still voltage potential, but that's the potential difference is how that's worded. Between the two plates, there's a potential difference. For example, if you attach these two plates to a battery, to a 9-volt battery, then the potential difference between the plates is supposed to be 9 volts. And that doesn't really mean that here it's 9 and here it's 0, but the difference between the plates would be 9. So, and you know, so here, for example, if that was 0, to make the math easy, then here the potential is 9, and over here somewhere is 8 and 7 and 6, and all the way down to 1 and 0. Okay, that's just a quick overview. I hope I wasn't standing in the way the whole time I was talking. I probably was. I'm not repeating it though. Claire, you're on your own, girl. All right. By the way, Claire, there are no pictures anywhere on the board right now. I'm just saying. I don't know why. I don't see any frogs or bees or dinosaurs. All right. What's next? Most of that we did yesterday. We were doing that V equals U over Q when we stopped. I think your equation sheet will say U equals QV. And it's got some other stuff in there that we'll get to as well, but that's the same equation as this. So if you see it, this is really a definition for V, but you'll see it written this way on the equation sheet, I think. Potential energy is QV. So it's important to note that if you multiply coulombs, that's Q, times volts, that's V, you will get joules. See, that's energy. Coulomb times a volt is a joule. 1 coulomb times 1 volt is 1 joule. So those units all work. They're SI units that all work. All right. Now, let's see what's next. Higher potential is on the left. We did that. Potential difference. We talked about that term. U equals QV. I should point out that V, potential, is scalar. That's a pretty important point. It's not vector. And you would have guessed that anyway. Everything in this equation is scalar. Nothing up here has a direction. U, all energy is scalar. Energy is scalar. And coulombs, Q, how much charge, that's scalar. So V is also scalar. It doesn't have a direction. It can be positive or negative, but that's not the direction. That's just the sign. Okay, we'll come back to that some more, quite a bit, in fact, hopefully today. All right, so we did that, we did this. I think I'm ready to mention there's another unit besides the joule for energy that we use sometimes with electrical charges. Now the joule is still the SI unit, but sometimes you're going to see a unit called the electron volt. And the symbol is exactly what it looks like. It's called the electron volt, and that's a symbol for an electron volt. It's not complicated at all. If you just think about what you're looking at. We already talked about the fact that energy is Q times V, where Q is in coulombs and V is in volts. Well, instead of the coulomb, what if you used the electron as a unit? One electron. You know that one electron then would have a charge of 1.6 times 10 to the negative 19th coulombs. Remember that number? That's the elementary charge. So what you could say is, for this unit, instead of coulombs, you're using electrons. So if something has this many coulombs and it has a potential of, let me erase that. It has this many coulombs of charge, like a proton does, an electron does as well. And let's say it's a proton though, so it's positive, and it has a potential of 1 volt, then that of course would be 1.6 times 10 to the negative 19th joules of energy, if you take Q times V. Well, if you're using, and that's joules, that's the SI unit, but if you were using electron volts, you would say, well, that's equal to 1 electron, and that's 1 volt. That's what we had there, 1 volt. And so that's 1 electron volt. So what you're seeing is this many joules is equal to 1 electron volt. Now, we don't really use the electron volts a lot in the rest of this chapter, chapter 19, but we are going to use it quite a bit in later chapters. So you need to go ahead and learn it. The electron volt is a unit for energy. You need to know that. And then it's really simple, just E is the charge of an electron. Okay.
That's all I'm going to say about that right now.
Now, let's move on to deriving some more equations that we can use for U and for V. All right, I told you that the amount of work you do pushing the particle from here to there, back to this example, pushing the particle to the left would take work because the field is pushing it to the right. So you do some work by pushing it. That's equal to its potential energy when it gets over there. We've already talked about that. Well, if that's true, then that's equal to force times distance, isn't it? That's what work is equal to, the amount of force we had to push with times the distance we pushed it. Well, with parallel plates, it's a little, the concept is the same, but we know we would never really use this equation for parallel plates. However, that's still equal to F. Maybe, because I can see without even looking, Julia, that you're getting confused. You're saying, well, if you don't use that equation with plates, all right, so we won't have plates. We'll do this instead. There's an electric field that goes out in all directions from the positive particle. So these are field lines. Well, immediately to the right, there is a proton. Now there's a field around this charged ping pong ball. Well, there's a proton here. The field is going to push it to the right, push it away. You take it with your hand and you move it to the left. So you're doing work on it, moving it to the left, aren't you? Okay. So you're having to apply a force and you're moving it through a distance. That's what we're talking about now here. Now the force you are applying really is KQQ over R squared, because you would use that equation with point charges. All right, so that's the amount of force you're having to push with. That's the force of repelling. So if you're going to move it to the left, you've got to push equal to that. This ping pong ball pushes it with that much force to the right. Well, if you're going to overcome that, you've got to push it with that much force to the left. Okay, so that's the force. The distance is the distance. You're going to push it all the way to the ping pong ball. So the distance is this. Well, that's R. That's the distance between the particles initially, isn't it? And so from that you can see the R, one of the R's would cancel there, and you come up with this equation that U, potential energy due to an electric field, that U is equal to K Q Q over R. So there is another potential energy equation. Looks a lot like Coulomb's law, except it's not R squared because it's force times distance, so it's just R. Now, that can be used, again, we don't really want to use that with parallel plates for the same reason we talked about don't use this with parallel plates, but it would work very nicely with point charges, like the drawing on the board. Another thing I mentioned just a moment ago is that this is scalar, which means it doesn't have a direction. Since it doesn't have a direction, we don't make this absolute value of the Q's, we put in the signs. If these charges are both positive, like in my picture here, then yeah, the Q's would both be positive. But if one of them was negative, then you just make it negative. So you can come out to be negative. Potential energy can be negative. If this particle here was an electron instead of a proton, now there's the force, KQQ over R squared, the force is the same, but it's attracting. So now if you're going, if you let it move to the left, you see if it moves to the left, but you're pushing to the right, that's negative force, so you're doing negative work on it. So this would actually calculate to be a negative number. Its potential energy right here is negative. Positive potential energy would be when the field's trying to push it away, but you're opposing that. Negative potential energy is just the opposite. Okay, so not absolute value bars. That's the only point I'm really making. Let me go now and show you what you have learned so far in terms of these equations that have a K in them. This is KQQ over R squared. That's Coulomb's law. You learned that last year even. That has the absolute value bars in it around the Q's because you get the sign of F just based on is it attracting or repelling. So absolute values. We also learned in the last chapter that E is KQ over R squared. And then we learned that, wasn't that it? That's the absolute value of the Q because you get the sign of E based on the direction. If you put a proton there, which way would it go? That's the sign of E. Would it move in the positive direction or the negative direction? So absolute value for the Q. Now we're getting, for the first time, an equation with K in it, but it's for a scalar quantity. So this is K, Q, Q over R. Notice how similar all these are. You're going to get them mixed up if you don't learn them. But these are both vector. F is vector and E is vector. They have directions. Now we come to U, which is scalar. And so you put in absolute value bars when it's vector. You don't put them in when it's scalar. So if you have a sign here, positive or negative, that's the sign of U.
What is the E beside the U stand for?
The E stands for electric. It's potential energy due to an electric field, as opposed to gravity. So you won't look at that U and think it's gravitational potential energy. Okay. Now we're going to derive quickly one more because V is the new thing in this chapter. So V, this is pretty simple. You probably already have done it in your head. Since V is U over Q, and U is KQQ over R, and that's over Q, then that Q cancels that Q, and you get V equals KQ over R.
Another one?
Another one. They're all very similar with just one slight difference. Each one of these is slightly different. Now V is scalar again, so I'm going to write the word scalar. And there's the V for potential or voltage, and it's KQ over R. Since it's scalar, you do not put in the absolute value bars. If Q is negative, then V is negative. Now, which Q is it? Is it the source of the electric field, or is it the test charge that's in the field? Which one was this? That was the test charge. So the test charge is what got canceled out. So the Q that's left in this equation, where there's only one Q, that's whatever's causing the electric field. And that was the same up here, if you remember, where there's only one Q, it's the source of the electric field. So that'll be the same. Anywhere there's only one Q, it's the source of the electric field. When there are two Qs, then there's the source of the electric field, but then the other one's the test charge that's in the field. Now remember we said for V, you don't even need a test charge. You can just have two parallel plates and there's V, there's potential between the plates, whether you put anything there or not. So that's why it makes sense to not have the test charge in this equation. You don't need a test charge, you just need a source of the field. For potential energy, if you go back to the parallel plates, if there's nothing between the plates, nothing has potential energy. You've got to have a test charge to have potential energy. It's got to have something in the field, and then the field gives it potential energy. But if nothing's in the field, nothing has potential energy. So you have to have a test charge there. So that part should make sense to you. All right, so you've actually got 4 equations now that all have K, and they have Q's, and they have R's. And you have to keep them straight. Yes.
Is V equals U over Q? That's test charge, right?
Yes, that's the definition of V, and both of these are for the test charge. U and the Q are for the test charge. Yes. If you remember the equation for E, that was F over Q. That Q is the test charge also, so that's the same. Now, one last thing before we leave that, the 4 equations there. I know you've looked in your equation sheet and it's right on the tip of your tongue. You're about to say, you know, the equation sheet doesn't write it that way. Aren't you? Have you looked?
Yes.
Yeah, it's different, isn't it?
Mm-hmm.
Yeah. You don't know how it's different, do you? It's okay. Claire, do you know how it's different? No, you have to look at your equation sheet, Claire.
You.
Pretending that she said something. In Physics 1, this equation was given that way, I think. But in Physics 2, that equation's still there, but it's not given that way. It's written this way for F. 1 over 4 pi epsilon. Q1, Q2 over R squared. It's written with that, instead of K, it puts that there. Do you remember we talked about that that's equal to K? And epsilon is the permittivity of free space. We used that in the last chapter. And what I told you then was, if you actually calculate this, because epsilon's a constant, you can look it up, 1 divided by 4 pi epsilon would be 9 times 10 to the 9th. That's what you would get. And so we just called that K. And in Physics 1, the College Board also calls it K. It's simple. But in Physics 2, because now it's Physics 2 and you're all smarter than you were last year, they decided, instead of putting a K there, oh, that's so easy, let's make it a little harder for the seniors. So we're going to write it this way. It's still 9 times 10 to the 9th. Okay, and I still know it as K. If you ask me for any of those equations, I'll tell you what it is in terms of K. But on your equation sheet, you'll see that written. 1 over 4 pi epsilon. So just remember that is equal to 9 times 10 to the 9th. I should probably actually look and confirm that what I'm telling you is true. Yes. And it has the F equation, it has the V's. That's on your equation sheet. This E equation, 1 over 4 pi epsilon Q over R squared, that's on there. The U is equal to QV, I told you, is on there, but it doesn't have this. Wait, does it have it somewhere else? U is equal to, your equation sheet writes it with deltas. Delta U is equal to Q delta V. But that's just U equals QV, the way I remember it. But it doesn't have the Q over R, sorry, not on there. It does have V equals 1 over 4 pi epsilon Q over R. It's got that one. So this third one in my list of 4, the third one's not really on the equation sheet. You'll just remember it. That's on the equation sheet though. Okay. In fact, if you remember that and you remember this one, you just stick another Q into that one and you got this one. So that would be easy to pull that one up from this and this. These two are on the equation sheet. Okay. That's that. All right. So again, I remember them this way. I talk about them this way. I'll write them on the board this way. But on your equation sheet, it's 1 over 4 pi epsilon.
Is that the same thing as like if the 4 pi epsilon was on the bottom of the R?
Yes, I wrote it pretty badly. It's the way it's printed is yes. Absolute value bars Q1, Q2. Absolute value in R squared is written like that. That's the whole thing. Yeah. Okay. Now, what do we need to do next?
We need to talk about more than one particle and what is the net V, or the net U, or the net E, or something like that. Let me see, I've got V as scalar, we talked about that. All right,
Let's do what I just said. I'm going to leave those 4 things up there so we can talk about them. Back at them. What if you have 2 particles, one's positive, and over here on the x-axis, here's a negative one. And I ask you, at the very middle, the very center point, whatever that is, where the distances are the same, it doesn't look the same, anyway, it's the same, at point P, I ask you, what is the electric field first? So you go back to the last chapter. Okay. Is it 0? No, that's just a yes or no. Is it 0 at point P? No. Because how do you get the direction of E? You place a proton there in your mind, and that one would be repelling it. This one would be attracting it. So they're both in the same direction. It would never be 0 at any point between them. And you're going to use, you'll use this twice. Once for that one and once for that one. Okay, now that was in the last chapter. What I'm doing now that's different is I'm asking you about V. Is V 0 at the midpoint? No? What do you think, Hannah? Yes or no? Is V 0 at the midpoint? V. No. What do you think, Claire? Is V 0 at the... Yes? Claire says yes. Did you say that, Claire, just because you're trying to be different from the other two? Or do you really think she really thinks it's 0? All right, let's see. If I was going to calculate it, V due to this one would be KQ. Let's say they're both the same amount of coulombs. I should have told you that before I asked you. Maybe that makes a difference. I don't know. Divided by R. Okay, and this is R. Which direction is V right here? Which direction is it? What direction is V?
Oh, it doesn't have.
It's scalar, it doesn't have a direction. I can't draw an arrow for V. You can't draw an arrow for either one of these. So there's no arrows, there's no direction. The Q though is whatever the sign is. So V due to that one is a positive number, whatever you could plug in the numbers for that Q and that R and K and get a number, but it would be positive. Q from this one, or V, sorry, V due to this one would be K, and the Q is negative. But the Q is the same, I told you, and the R is the same. And so that would be a negative number. So is it 0? Is V 0 at the midpoint?
Yes.
Yes, because positive and negative would add up to, because they're the same. Because I told you the Q's are the same and the R's are the same. So the magnitude's going to be the same, but one will be positive, the other negative. They will add up to 0. There is no direction. There is no placing a proton, which way would it go, none of that. For V, it's scalar. You just add up the two V's, whatever they are. And if it's right in the middle and the Q's are the same, they would be the same, but opposite signs. All right, you got that? So V right in the middle is 0, but of course E is not. Now, if I ask you, if I change it to this, now they're both same Q, same, but they're both positive. The R's are the same too between the particles and point P. Now, I've got these two things, E and V. Is either E or V 0 at point P? If so, which one or ones are 0? Is E 0? Well, let's do it. We'll do them one at a time. Is E 0 at point P? Hannah says yes. Julia says yes. Claire, what do you think? Claire says no. You didn't say no, did you? The answer is yes. Yes, it is 0. How do you know, Hannah, that it's 0 here?
Because like the fields would cancel out.
Yes, the field is the question, and remember you get that by placing a proton there in your mind. That one would repel it, this one would repel it, and everything's equal in the equation. The Q and R's are the same, so in their opposite directions. So now E at the midpoint is 0. Remember last time it wasn't because they're in the same direction. Is V still going to be 0 right at the midpoint? What do you think, Julia? Yes or no? Would V, due to both of these charges, would V be 0 at the midpoint? Yes or no?
No.
No, and you said no also, Hannah, didn't you? You said yes?
No.
No, you said yes. I'm confused.
I said no.
You said no. Claire, you said no as well. Claire's getting them all right. Because there are no vectors to draw, so it's not opposite directions, there is no direction. It's not the absolute value of Q, you put it in, well now they're both positive, so if you add them up, two positive numbers would never add up to 0. So you know it's not 0. It would be this plus this. It would be KQ over R plus KQ over R. You just add them together. They're both positive because the Q's are positive. Okay, you get the idea of the difference between E and V? You think totally differently about a vector quantity that they have a direction, and a scalar quantity they don't have a direction. If I was to ask you about U, now you've got to put something, you've got to have a test charge in there somewhere. So if I put a negatively charged, I put an electron right there. And does it have potential energy right here, or is its potential energy 0? Potential energy, the net potential energy from both of them. Well, you would go KQQ over R, and it's not the absolute value, so that Q would be negative, or that U would be negative because one of the charges is negative. And then you do it again for these two, well, that's negative also. So the net U would be negative. You just add them together, but it'd be negative. A negative plus a negative. Okay, so you're getting the idea of how to use these equations. That's what we're doing today.
Yes, we are. Pretty clear. You can get it. All right.
Work done. We're going to do this last thing, at least mention it. Conservation of energy, we've already talked about that. If you have an electric field that's in this direction, I don't know what the source is, over there somewhere there's a source. And I have a positive particle and I just place it there. If I let go of it, which way would it move? This is all review right now. Which way would this proton move? Left or right? Or up or down?
Right.
It would move to the right. So if I take it, no, let's say I just let go of it and it moves to over here somewhere. And this electric field is constant, okay? These are field lines. So I let go of it, it moves over to here. Was any work done on it? Was any work done on it by anything? Yes. What did work on it? The electric field did. I didn't do any work on it. I placed it there and let go of it, and I walked away. But the field applied a force and moved it through a distance. So yeah, the field did some work on it. Now here's I guess, I'm not sure I know how to teach this, but I'm going to try. The work is equal to the change in U. All right, that's just conservation of energy. If it has a potential energy here and it has a different potential energy there, then something did some work on it. You know what would be better for this illustration? What time's the bell ring? You don't know?
I think 54 or 50.
So we don't have much time left, do we? Let's say it's due to a point charge, which it works better for those equations anyway. So the field is that way, but it's also that way and that way. So it's getting weaker as you move to the right. The field, there's still a field, see? But it's getting weaker as you move to the right. However, it's still in the field, so the field is pushing it to the right. So obviously the potential energy is decreasing because it's getting farther away from the source. Well, W is equal to the change in potential energy. And the change in potential energy would be simply KQ over R minus KQ over R, right? So that's the potential energy here and that's potential energy there. What makes this a little tricky or a little different, not tricky really, but a little different, is that this would be the potential energy in the first position and this would be in the second position. Most of the time, delta anything is the second one minus the first one. We've done delta V, we've done delta U, we've done delta lots of things. And it's always the second one minus the first one. But if you want to know the work done by the electric field, then if you reversed it, if you did 2 minus 1, which is what we would think, everything is 2 minus 1, the second one is less, isn't it? There's less potential energy here because it's farther away. So if you did 2 minus 1, you'd get a negative number. And the work done by the field is not negative work because the field's pushing it to the right and it's moving to the right. That's positive work. So that's the reason it has to be, in this case, 1 minus 2. Because the force of the field and the direction it's moving are the same. So it's doing positive work on this particle by pushing it to the right. And if you get positive work, you've got to subtract it 1 minus 2 in that order. Now, if you forget to do it 1 minus 2, you can do 2 minus 1, but when you get a negative number, just realize, oh, it didn't do negative work, and make it positive. That's the same thing. Okay, we're gonna come back to this. Conservation of energy, we have a lot to say about that. We'll come back to that Monday, but we'll stop here today. Your homework again is B. Your homework, Claire, that you missed was assignments in chapter 19, A, and now B is due Monday. Even though you probably won't get this video until Monday. All right, signing out. Thanks. Nice to have spent the time with you, Claire. How do I turn it off? I think I pushed that.